Mm. Mm. Okay. Is it okay, Anand? Anand or Chaitanya? Anand.
Yeah, good afternoon. So we are going to start in 5 minutes.
Good afternoon, Jasti Garu.
Good afternoon, Andy. So we are going to start in 5 minutes.
Yeah, YouTube live stream mane కొంచెం చేస్తే we'll start.
It's a breakout in noise actually. इसके share screen.
Yeah, no problem. No problem. You just go ahead. Okay, we start. Good afternoon, guys. Let us welcome our guest. Our guest today. It's a pleasure for me to introduce the speaker, Dr. Jasti Sriranga Chaudhary. Is a scientist at Indian Institute of Tropical Meteorology, India. He completed his master's from Tellakula Jalaya Polisetti Somasundaram College, which is affiliated to Nagarjuna University, Guntur. So he completed his MTech Atmospheric Physics from University of Pune. Prior to joining 5ATM, he received a PhD degree in Atmospheric and Oceanic Sciences from Savitri Bai Pune University, IITM Pune, in 2007. Later, he went to the International Pacific Research Center, IPRSC, University of Hawaii, USA, as a postdoctoral fellow from 2008 to 2011. Primary work on is hello. Some disturbance is there. Some disturbance is there. Its primary work is mainly on monsoon climate variability and physical oceanography. Dr. Jasti Chaudhary published more than 80 publications so far, and he contributed understanding of the teleconnections from tropical oceans to Indian summer monsoon. One of his best findings on the relevance of the decay phase of El Nino for the predictability, variability of the Western Pacific and Indian Oceans is one of the highly cited paper with the 350 citations, and he was the first to identify the existence of the westward propagating barrier layers and westward propagation of the warm temperature anomalies along the slope of the thermocline over the South Tropical Indian Ocean during ENSO and IOD events. These processes led to the change in the AC interaction over the Western Tropical Indian Ocean, which is a region crucial for the Indian summer monsoon prediction and the development of the MJO activity. He received a couple of best paper awards, and he participated in several conferences, and two PhDs are awarded under his able guidance. So today he's going to present a lecture on the Indo-Western Pacific summer climate variability and impacts on the Indian summer monsoon. My dear students are the participants. This is a very important topic in the present scenario. Even though we have acquired a very good knowledge on monsoon, but still there is a lot of things to explore to identify the connection between the monsoon transition system, planetary scale circulation, and its teleconnecting parameters. So hope this presentation will further add your current understanding of the monsoon. Let us welcome Dr. Jasti Chaudhary. Sir, uh,
Uh, Good afternoon to all, and thank you, ma'am, for a nice introduction. So, am I audible?
some disturbance is, some echo is there, sir. Some echo is there. I don't know where we are getting. Uh, Mr. Anand or Chaitanya, can you please respond on this? Hello?
Uh, it is clear for me, ma'am.
Yes, it's okay now.
Yeah, and is it visible? So, screen
Yes,
presentation.
yes,
Yeah,
yes,
okay, sure. So, I'm going to start, and then.
yes.
Yeah, thank you, ma'am, for a nice introduction. So today I'm going to talk about the Indo-Western Pacific climate variability and impacts on Indian summer monsoon. So it has been known for long that Indian summer monsoon variability is highly tied with ENSO, so especially developing phase of El Nino. But it is not just developing El Nino, so other phases of El Nino can actually influence the Indian summer monsoon. So let us see what is that. So here, outlines of my talk are like, I'll give some background on the Indo-Western Pacific ocean capacity effect and its influence on the Indian summer monsoon. We'll have discussion on that, and then I will also talk about the ENSO decay variations on Indian summer monsoon rainfall, and I will just touch upon the Pacific Japan pattern impact on Indian summer monsoon. So, of course, it is needless to say what is like importance of finance monsoon. Here we know that it is very important for economy and ecosystems, and ISM contributes around 80% of total annual rainfall, and it affects like when you have floods or droughts, it has a huge impact on agriculture. And the forecasting ISM is always very important, and it is mainly for the planning and improve food and drought safety programs, etc. So the dynamical prediction of Indian summer monsoon skill originates mainly from the fact that monsoon strength is tightly linked to teleconnections. So a number of climate modes that can influence the Indian summer monsoon on year-to-year variability. So a deep physical understanding of different climate modes and their interplay or interaction with ISMR is the foundation for improved predictions and projections. So globally, if you look at this interaction, so a myriad of large-scale atmospheric and oceanic coupled phenomena influence the spatio-temporal complexity. So we are not just talking about the all India mean summer monsoon rainfall. So here spatial patterns are very important. So though some of those drivers are coming from locally, like depressions and MJOs from Indian Ocean and Southern Oscillation, and so Southern El Nino Southern Oscillation, and Indian Ocean dipole, Indian Ocean warming. Eurasian snow can have impact on the monsoon, and on the decadal time scale we have PDO, IPO, and AMO, etc. But when you come to the region of Indo-Western Pacific, we have most major components are like that can have a lot of variations that are due to ENSO, like El Nino Southern Oscillation, and we have the Asian Australian monsoon that includes cross-equatorial flow of Indian summer monsoon and Western North Pacific circulation, and we have Indian Ocean dipole, and Indian Ocean basin-wide warming can also influence the year-to-year variability of Indian summer monsoon. So these systems influence rainfall variability throughout the tropics, not just over the Indian monsoon region and even in subtropics. So understanding their behavior and interplay is critical for rainfall forecast. So here you can see a schematic diagram where number of drivers are placed. For example, year-to-year variability, whatever you see in yellow boxes, starting from canonical El Nino Monoki, El Nino Decay and Tropical Indian Ocean warming, Equino, Indian Ocean dipole, Atlantic Nino, snow cover, and PJ, Pacific Japan pattern, and IPOC mode, and South Asian high variations can influence the Indian summer monsoon, southern angular mode can influence the Indian summer monsoon rainfall, and subtropical deserts expand or contrast, whatever. So that changes even to albedo can influence the Indian summer monsoon rainfall. So there are the pathways are provided on the top of like those panels, and the blue is
Jastiji,
uh,
just
uh,
a small interruption. Sorry.
yeah, yeah,
Your voice is not properly audible. Okay, you
okay.
just check the mic.
Uh,
It is not
now
clearly
it's
audible.
now
Yeah.
now it is fine.
Yes.
Is it okay? So okay. Okay,
Okay.
so this is a schematic of monsoon drivers. Is it fine now?
So some disturbance is there. Some echo is there. Some
I
echo is
don't
there.
know. I don't have any. Okay, I will just unplug and plug it in. So, hello.
Yeah. Yeah.
Yeah, is it okay now?
Yes, sir.
Okay. So this schematic shows the some of those climate drivers, like starting from canonical El Nino to subtropical deserts on the interannual time scale, and you have a couple of or more than this. You have some drivers that can influence the decadal variability of monsoon, like PDO, AMO, and on the climatic change point of view, you have global warming and aerosol forcing can influence the Indian summer monsoon. So here I'm going to discuss on year-to-year variability, mainly focusing on two aspects. One is ENSO decay, and another is PJ and IPOC mode. Um, in general, El Nino developing phase exhibits large impact on Indian summer monsoon rainfalls. That is very well known. So positive SST anomalies in the Central Pacific alters both descending and ascending branch of like water circulation, which is known to be a main driver, like connecting the El Nino to the Indian summer monsoon. And some studies suggested that convective activities over Northwest Pacific is an important component that bridges ENSO monsoon teleconnections. And And so, anomalous low-level circulation over the western North Pacific that I will show you where exactly can influence the Indian summer monsoon during developing phase of El Nino. So, when it comes to ENSO effect on the Indian summer monsoon, so it can be through the changes in atmospheric circulation over the not only tropical Indian Ocean but also from the western North Pacific region. So apart from El Nino developing phase, that is very well known. So recent studies highlighted the impact of El Nino on El Nino decay on Indian summer monsoon through tropical Indian Ocean SST warming. So in general, if you see this plot where dashed line represents the autocorrelation of Nino 3.4, so you just take DJF or NDJ Nino 3.4, and you can correlate with Nino index for a 2-year time scale. So what you can see here is El Nino is developing around 4th month or 4th to 6th month. So that is developing phase of El Nino and then just before the monsoon season. So you have El Nino developing in the just before the monsoon season, and hence there is a kind of significant anomalies in the Pacific that can influence the monsoon in developing phase. And as you go on to the peak phase, by 12th month, say December, you have a peak El Nino seen in the Pacific, and at the same time, you can see the tropical Indian Ocean and the South China Sea. SST is also warming along with the El Nino. So the warming is lagged. That means the El Nino is inducing SST warming in both tropical Indian Ocean and South China Sea. But when it comes to decay phase, when once El Nino start decaying, you can see that by next year, May or June, but tropical Indian Ocean warming is still persisting. You can see the shaded region where in the circle. So once ENSO is gone completely by mid of next summer, and that tropical Indian Ocean warming is still alive. So this is an important point that we have to really care about the tropical Indian Ocean warming regarding this monsoon variability. So why we should bother really about this tropical Indian Ocean warming and decay phase? So here is a figure. You can see the first one is a EY of 1 of Indian summer monsoon rainfall, where you generally see like countrywide unipole, except in the northeastern parts. So you can say it is a dry anomalies. This is highly associated with ENSO that you can see in the figure C, where the PC is correlated, lag correlation, and when it comes to year 0, they are highly correlated with the pattern what you are seeing in figure A. That means the dry or wet anomalies in the Indian monsoon region are highly correlated with ENSO. And the second one, when you see there is a dipole-like pattern in the EOF pattern of rainfall. So there can be opposite pole between monsoon trough, especially eastern parts of trough and southern Indian Ocean. And this pattern is highly correlated with North Indian Ocean warming that you can see the pink one peaking year 0. And the corresponding anomalies also we can see in figure F, where you can see tropical Indian Ocean warming along with there is an anticyclonic circulation over the western North Pacific. So definitely tropical Indian Ocean warming on the interannual time scale is important, not just on the climate change point of view. So when we start with El Nino peak phase, when you have strong El Nino, you do see warm anomalies in the eastern and central Pacific, where you expect to have a strong convection, and then when you have strong convection, you have an upward branch of Walker circulation there, and corresponding downward motion or substance is located over the maritime continent and tropical Indian Ocean. Where so because of this subsidence, the shortwave radiation can be high, and it can warm the tropical Indian Ocean and along with ocean dynamics. So for long, actually, tropical Indian Ocean SST has been long been dismissed as a passive on the ground that rainfall decreases there at the peak. Actually, if you see in the DJF, generally rainfall is low over this particular region. But does the TIO remain passive in subsequent seasons? So that is an important question. So when you look into the evolution of both tropical Indian ocean warming and El Nino, so figure A shows that in the developing year of El Nino, so you could see warm anomalies in the El Nino region and convergence there. And as you go to next season, SON, where ENSO is getting stronger, El Nino is getting stronger. At the same time, Indian Ocean dipole is seen in the Indian Ocean. And as you go to peak phase of El Nino, that is in DJF, so El Nino related warming is very high and strong convergence is seen. At the same time, IOD is gone and you have basin-wide warming in the tropical Indian Ocean. So that warming is persisting till next summer. You can see clearly in the figure E. And but by the time of next summer, El Nino is gone. So now tropical Indian Ocean and Western North Pacific warming are apparent here. Along with this Indian Ocean warming, you can also see that there is anticyclonic circulation developing in the peak phase of El Nino in the Western North Pacific, and that anticyclonic circulation is persisting till summer, that means 3 seasons. So this is a important point here that SST can persist, as we know that ocean has a kind of ocean anomalies can persist for a long time, but how atmospheric anomalies are persisting for 3 seasons is an important point here. So this can be explained via this schematic diagram. When you have El Nino peak phase in the Pacific, you can see that warm anomalies in the red curve. And when you have strong warming here, that means you have heat source kept at the equator. When you have strong heat source, just you would see that cyclonic circulation is developing in the northwestern part of that as a part of Stono pattern. And when you have this strong cyclonic circulation, northwest of that cyclonic circulation, you will see that northeasterlies. So these northeasterlies are superimposed on mean northeasterlies of Pacific, and then that actually intensify the wind. So when the winds are very strong at this, well,
Mr. Pradeepa Chinnaswamy, please mute yourself.
shall I continue?
Okay.
Yeah, so when you have strong northeasterlies here, mean northeasterlies are superimposed by anomalies, it would enhance the mean winds, and then you have latent heat flux released to the atmosphere is high, and you have strong cooling over the central parts, like just north central parts of the Pacific, and that cooling actually induce anticyclonic circulation to west of it as a Rossby wave response. When you have this anticyclonic circulation and west of it, you will have southwesterlies which actually are opposite to the northeasterlies, and then you have warming over that region. On the other hand, in the same during the peak phase of El Nino, you have strong subsidence over the maritime continent and eastern Indian Ocean that actually induce anomalous anticyclonic wind stress curve south of that. That wind stress curve can generate downwelling Rossby waves there that can propagate to the west. So some disturbance. So propagate to the west in the subsequent seasons that we can see here. In by MAM, the ENSO is getting weaker, but Northwest Pacific, Central Pacific cooling is strengthening. So the cooling alone can maintain the anticyclonic circulation for the Northwest Pacific, and these winds can even extend to tropical Indian Ocean. And as you have warming over the Southern Indian Ocean due to these Rossby waves, that can even converge there. So you can see she-shaped kind of winds here. And when it comes to JJA after ENSO, and you don't see a cooling over the Pacific, so anticyclonic circulation is still seen here. But by the time tropical Indian Ocean, North Indian Ocean is also warmer because these northeasterlies are associated with anticyclonic circulation in the north of the equator or the tropical Indian Ocean, in the Northern Indian Ocean, are opposite to the southwesterlies. That means southwesterlies are weaker, and hence the latent heat flux released to the atmosphere is low. So you will see that there is a warming in the maintained in the tropical Indian Ocean. So you have southern Indian Ocean due to Rossby waves, northern Indian Ocean mainly because of heat fluxes. So these processes actually maintains the basin-wide warming. Now, how this basin-wide warming can maintain this anticyclonic circulation that we can see here in the next plot. This is with additional circulation patterns. So if you look at the figure D, when you have a tropical Indian Ocean warming, what you would expect is a deep convection. Now, ENSO is gone, and so you have warming only over the tropical Indian Ocean. That means these tropical Indian Ocean anomalies are active, unlike in the peak phase of ENSO. So when you have deep convection due to this warming, you would see the tropospheric temperature is warming due to just a deep convection. When we have that latent heat flux released to the atmosphere is high, so you would see that there is a strong tropospheric temperature over the tropical Indian Ocean, and that at the equator can propagate as a Kelvin wave towards the Western Pacific. So once you see the Kelvin wave or the equatorial region, east of it you would expect a kind of strong easterlies. Those easterlies are stronger at the equator, and as you go away from the equator, they are weak. So you create a kind of anticyclonic curve, and so you can have a kind of anticyclonic circulation. So due to the Ekman divergence, so you would see that substance happening just above the PBL, and when you have that, there is a suppressed convection over the Northwest Pacific, and so this suppressed convection and circulation feedback can enhance the anticyclonic circulation. So in total, what you would see is tropical Indian Ocean warming in the subsequent summer can maintain the anticyclonic circulation without any Pacific anomalies through Kelvin wave Ekman divergence mechanism. And here, what you would see another circulation is just north of this anticyclone is a cyclonic circulation, which is part of Pacific Japan pattern. So and this coherent evolution of tropical Indian Ocean warming and Western North Pacific anticyclone, and their variability is nothing but Indo-Western Pacific capacitor mode. So why we should call it as a capacitor mode? We can take a look at this schematic again. So once we start with ENSO, let us consider the ENSO as a battery in circuit. And once ENSO started its influence onto the Indian Ocean, so most of the time IOD develops in September, and then once IOD is gone by December, basin-wide warming due to ENSO. So here ENSO is charging the capacitor, and once ENSO is gone, so that means battery is discharged, but still basin-wide warming is persisting, and not only persisting, it is also maintaining the Western North Pacific anticyclone. That means when the charge it is get discharged, battery is over, so capacitors start reacting. So this is how we can call it as a Indo-Western Pacific capacitor effect, where is actually triggered by ENSO. So this is not just only related to ENSO. Using coupled model experiments, Kosaka et al. Showed that this IPOC mode or PJ pattern can even evolve without El Nino. So, for example, this particular year, 2020 monsoon, I will show some slides on that. So overall, when you look at the in observations, the summer after El Nino, you would see that Indian Ocean is warmer and we have strong anticyclonic circulation over this region. So this anticyclone feedback positively to PIO warming through by weakening the southwesterlies, and again this PIO warming can feed back to the Western North Pacific anticyclone. So there is a positive feedback and there is a interaction. So actually this is all triggered by ENSO but maintained by positive feedback between Western North Pacific and Indian Ocean as a interbasin interaction. And what exactly is the PJ? So here PJ is the Pacific Japan pattern, teleconnection pattern, is dominated pattern of interannual variability for the Western North Pacific and East Asian monsoons. And the PJ pattern features a dipole or tripole that you can see in 850 HPA vorticity anomalies in the Western North Pacific. You can see wave-like pattern with high, low, and high, low, etc. is from south to north, equator to subtropics, and which is clear in vorticity, and SLP corresponding to this vorticity. You can see SLP also showing that. And most importantly, when you have a strong PJ pattern in the Western Pacific, Western North Pacific, you would see it has strong impact on the air temperature. There are many studies saying that the heat waves are strong when you have PJ pattern on the East Asia. Also, you could see that there are rainfall anomalies strongly influenced, especially Japan gets flooded when you have a positive PJ pattern. And this PJ pattern can actually modulate your zonal as well as meridional circulation. For example, you see that average between 5 and 25. In the figure A, you can see there's red colors. Across the longitude, if you cut, what you see is a subsidence over the anticyclonic region and a kind of upward motion in the monsoon season, but it is south of southern Indian Ocean region, southern Indian region. And is the meridional circulation also highly influenced because anticyclone cyclonic circulation corresponding to that 10 to 20 you see a subsidence, and north of that you see upward motion somewhere in Japan, and then north of that again subsidence, but it's weak. So it can modulate both zonal circulation as well as the meridional circulation. So using coupled model experiment, as I mentioned, so in this particular paper, Kosaka et al. Used coupled model, and you can see that observations in right hand side figure A. So when you have ENSO and tropical near motion is warmer, and even it is reflected in coupled model. But in the another experiment, what they have done, they have just removed the ENSO and prescribed climatology there. So that is what you can see, no ENSO case here in the peak phase. So that means there is no ENSO in the model. But even then, you can see that figure F, where even then there is no ENSO. If you look at the variability of Indo-Western Pacific, you would see that warm anomalies, some of the some parts of the Indian Ocean, and cold anomalies in kind of Northwest Pacific. So, and apart from that, you can see the left hand side, no ENSO, there is a kind of PJ pattern developing in the model. Even if you take climatological SSTs, just run your atmospheric model for 200 years, take the variance of 850 HPA vorticity in the Western North Pacific, what you get is a PJ pattern. That means this PJ pattern or IPOC can develop even without ENSO, and it is kind of due to the internal variability of the atmospheric dynamics. And here, how the IPOC can influence rainfall or the Indian monsoon is discussed. This IPOC impact on the East Asia and Western North Pacific is very well known. So here we have used some coupled model experiment to find out what is the contribution of tropical Indian Ocean and Western North Pacific anticyclone. So various data sets are used. So basically, we can get this IPOC pattern using SVD analysis. So we have to consider two variables. One is the 850 HPA vorticity over the Western North Pacific and tropical Indian Ocean. So when you consider two components and get your leading mode, what you would see is the IPOC pattern with warming in the tropical Indian Ocean and anticyclonic circulation and easterlies to the in the Bay of Bengal. And corresponding PC is in blue color. You can see in figure C. And when you correlate onto the Indian summer monsoon, what you would see is a opposite pattern with the Indo-Gangetic plain, especially eastern parts, getting a negative rainfall, and south of it, like southern peninsular India, has positive rainfall. Also, we can see some kind of positive rainfall in the northeastern region. So the index is prepared based on this. So negative rainfall box minus positive rainfall. So you can see it is in blue. So they are obviously very highly correlated. That means this IPOC can have impact on the Indian summer monsoon by inducing this kind of dipole pattern. And this study by Misra et al. Have come up with very excellent analysis saying that the combined mode suggesting that ENSO El Nino related anomalies are highly influencing the rainfall over the Indian summer monsoon region, as we have seen in the EUA of 1. So this is very well-known relationship. But in the second EUA of what they got is the North Indian Ocean warming and kind of dipole pattern here. But what they have pointed out is that it is not obvious why abnormal warm North Indian Ocean during these summers should favor suppressed monsoon rainfall over Gangetic plain. It can enhance, in general, if you have a tropical Indian Ocean warming, it should enhance the rainfall. But it seems more likely that physical link between ENSO cycle and ISMR rainfall anomalies in subsequent summer is through atmosphere, but they have not mentioned what exactly is the link. So our study suggests that the missing link is the physical link is nothing but IPOC. So how we get this tripole pattern? That is an important question. So you look at these figures again, regression of the SVD-PC1 upon SLPs and tropospheric temperature in the first panel, and second panel moisture divergence and transport, and third panel is the velocity potential and 200 HPA velocity potential and divergent wave. When it comes to the positive rainfall in the southern parts of India, so the TAO warming induced by strong easterlies from here, because we have strong easterlies, as I mentioned, NIO can be warmed because latent heat flux from the ocean to the atmosphere is low. So in the southern flank of this anticyclone, and the moisture convergence enhances the convection over this region. So you would see that blue colors, this is the moisture convergence. Basically, the southern flank of anticyclone associated easterlies and the moisture convergence causes rainfall to enhance here. Not only that, rainfall also influenced due to response of the deep convection over the maritime continent. When you have strong again heat source here, the Rossby wave can propagate west and you can have a maximum rainfall there. So that is what also can happen. So these two mechanisms actually cause rainfall to enhance over this southern parts of India. And when we come to the monsoon trough and especially eastern parts, the anticyclone is part of like a PJ pattern that we know, and then that can actually excites a westward propagating cold Rossby wave, which is associated with the suppressed convection that you can see here, and moisture divergence over this region and dry moisture transport, these combinedly causing negative rainfall in eastern parts of this monsoon trough. And just north of that, you have positive rainfall. It is obviously due to the northern flank of this anticyclone converges there, and you get kind of tripole-like pattern. And that is also highly supported by large-scale circulation with upper level convergence, lower level divergence in the winds. So one might question even like there are weak monsoon winds, but why there is a positive rainfall in the southern parts of India? So despite a weak monsoon circulation, strong low-level moisture transport and reduced moisture stability associated with Indian Ocean warming can increase rainfall over there. So just to say kind of application of this study, this year if you see is happening now. What you see is till 13th, like yesterday, we have well distributed rainfall in the mean, but when you see with respect to normal, when you take anomalies, what you would see is kind of what we discussed till now. So high rainfall in the southern parts of India and negative rainfall. You can see the red colors are negative rainfall over the monsoon trough region. North of that, bit of positive. I don't want to say exactly going with the IPOC, but 90% pattern is going with the IPOC pattern. You can see the rightmost one. So this is a response of rainfall to IPOC mode. So here colors are exactly different, like opposite. Blue is negative and red is positive in our plot, and IMD it is red is negative and blue is positive. So I strongly feel that this year monsoon till now, at least JJA, is highly influenced by IPOC like pattern. That is what you can see here. We have run the CFS V2 with February ICs. Even then, just 4 months before, like 4-month lead forecast also shows that there is kind of anticyclonic circulation evolving over the western North Pacific and easterlies coming from there. And you have southern India getting better rainfall and slightly low in the monsoon trough region as you compare to south. So it shows that IPOC mode is predictable and its influence also predictable, at least in CFS in this particular year. And sorry, yeah. So when you go to next one, so this is we want to prove, like we want to show, we want to see how this Western North Pacific anticyclone and tropical motion are contributing, how much is contributing to this dipole mode. For that we have used CFS V2, and here CFS V2 is able to capture IPOC mode that you can see in SST as well as rainfall 850 HPA winds. With that we have used model to examine the impacts. So in experiment 1, what we did was that we have selected a year, that is 1990, because during 1990 there is no ENSO, so there is no Indian Ocean dipole, so it's a kind of normal year. And in the main initial conditions, we have prescribed cooling over the Western North Pacific to generate anticyclonic circulation. So when anticyclonic circulation is only generated, what you can see in the model is a kind of low rainfall in the monsoon trough region and high rainfall in the northeastern parts. And when you prescribe only tropical Indian Ocean warming in the model, in the experiment 2, what you see is kind of high rainfall over the Western Ghats and other parts of India. When you consider both tropical Indian Ocean warming and Western North Pacific anticyclone, what you would see is kind of PJ pattern type rainfall pattern with enhanced rainfall in the south, slightly low in the middle, and again in the northeast there is a positive rainfall. So In this experiment, TIO warming contributes to the positive rainfall about 80% associated with the IPOC made over Western Ghats and the Arabian Sea, and low rainfall over the monsoon trough region and high rainfall over the Sundarban or even northeast regions are not represented only when TIO is considered, that you can see, but they are very well captured when we consider anticyclonic circulation. This tells you the story that how important is IPOC mode and what exactly the component that is influencing the spatial pattern of Indian monsoon rainfall. So all these things we put together in a schematic, and we can see here is the rainfall what is shown in the shaded region with very suppressed rainfall over the Western North Pacific continued to monsoon trough, eastern parts of the monsoon trough, and enhanced rainfall on either side. So when you have strong anticyclonic circulation, including PJ pattern, that you will have easterlies there, and the cold Rossby waves can suppress the rainfall over the monsoon trough region. And the north of that, enhanced convection due to the again deep convection maritime continent and convergence south of this anticyclonic easterlies. And tropical in-motion warming and can trigger the Rossby Kelvin wave at the equator, and then it can propagate to the western Pacific, and that actually influence the maintain the anticyclonic circulation. So it is not only just talking about the only El Nino impact onto the developing phase, but you have other components that can strongly influence the Indian summer monsoon other than ENSO. And here, this IPOC mode teleconnections to the Indian summer monsoon also not stable with time, as we see El Nino monsoon teleconnections. For example, you see this picture 86 to 2014, when you have extracted the IPOC mode from there, the PC1 is again correlated with the rainfall. What you would see is kind of dipole, not tripole. So this trigger, it made us think, is this response is stable in the time. So when you look into precipitation index and SVD PC1, 21-year sliding correlation, you can see in the right side figure. So you would see that in some, these are different rainfall data sets are used to find out the robustness of signal. So all data sets are showing kind of similar results. So here in one epoch, the relationship is positive, another epoch it is weak, and third epoch it is again positive, suggesting that this epochal change in the IPOC monsoon relationship. And why exactly it happened? So we have addressed that question here, and this is the epoch which is having a tripole-like pattern from 76 to 2007. If you extend to 2009, you would get the same results. So in this particular epoch, as I explained, moisture divergent and other mechanisms responsible for maintaining this tripole-like pattern. In the second epoch, in the right side, you can see that there is kind of disturbed pattern in the rainfall over the Indian monsoon region with mostly negative rainfall. And associated IPOC, you would see that tropical ocean is warmer and anticyclone is slightly shifted towards northeast when compared to epoch 3. So, and associated with that, moisture divergence is seen most of the Indian subcontinent, and unlike in the epoch 3. Therefore, you would expect that negative rainfall over the Indian subcontinent. So, how these anomalies are triggered? Now, when you look into the lag correlation of PC with SSTs, so from DJF to JJA. So in the first epoch and all three epochs, you would see that El Nino is strong in DJF, but as you come to the second epoch, in the MAM, what you would see that El Nino is slightly weakening in the first and last epochs, and but in the second epoch, it is not very prominent. When you go to JJA, so what you see in second epoch, central equatorial Pacific SSTs are warmer compared to other two epochs, and it is not eastern equatorial Pacific. So when you plot anything with 3.4, you would see that El Nino seems to be decaying, but when you plot 4 region, what you would see that is persisting. So because of these anomalies, there is strong convergence, and the anticyclone is slightly moved eastward, and along with that you have a PDO kind of cooling in the central Pacific, central North Pacific. So these two anomalies actually disturb the IPOC pattern in second epoch. So this there is a decadal modulation or epochal modulation of IPOC impact onto the Indian summer monsoon. We looked into CMIP5 models to see these signals are robust in these models. So we have selected kind of 22 models, and out of that, those red colors are the models which are actually capturing IPOC mode very well. So these are the models which I have shown in the red colors. So you see in all these models, turbulent motion warning is seen, and anticyclonic circulation over the Northwest Pacific is also apparent. But there are some differences in the Eastern Pacific. Some shows cooling, some shows neutral, and some others shows kind of warming. So when you look at the teleconnections of this IPOC mode with Indian summer monsoon rainfall in these models, in observations you could see that in figure A of right hand side dipole pattern, but even first model shows no clear signals, and second model shows yes there is kind of dipole. So here only a few models are able to represent the dipole pattern in rainfall, kind of last figure you can see, but most of them are not able to actually represent the dipole or represent the teleconnections between this IPOC and Indian summer monsoon. So when we consider only those models which are doing well, so we have composited them as a proper model. That means which have a better teleconnections indicating the dipole-like pattern in the monsoon rainfall associated with the IPOC. So you would see that A and B shows the proper model ensemble mean, MME multimodal ensemble, and right hand side what you see improper models. They have IPOC but they can't represent the teleconnections to the tropical our Indian summer monsoon rainfall. Basically, this is because you have a weak IPOC mode in improper models. So you could not see this kind of response to the Indian summer monsoon region. And though in the proper models, we just go on to look into interdecadal variations of IPOC and the Indian summer monsoon, what we would see, some models are able to show kind of this decadal modulations with strong relationship in some epochs, and other epochs it is quite weak. So this is all about the IPOC, but there is a extension of that. The IPOC can be highly dependent on ENSO decay. So ENSO decay has a lot of variations. So like what you see here is that El Nino cycle for kind of 6 events from 58 to 2003. So what you see when there is El Nino developing, they are almost converging. So standard deviation among these events, what you see in the x-axis is the calendar month, and the y-axis is SST anomaly. This is the SST anomaly composite. I think each individual year, and the composite is in pink color, the mean. So standard deviation while developing phase, you could see that standard deviation is low. That means you won't see too much variations while developing the ENSO. But when you see peak phase, definitely there is a high variance or standard deviation. But high compared to in developing ENSO and peak El Nino, what you see SD is very high, standard deviation is very high in decay phase, suggesting that there is a lot of modulations in the decay phase of El Nino when you compare to the developing and peak phase. So it is always important to look at how these different decays are influencing Indian summer monsoon rainfall. So we have considered historical data and we have divided them into three categories. One is early decay. That means the El Nino is decaying before like around spring and come over like it is translated to the La Nina in the Pacific. And in the mid-summer decay. So this kind of decays are happening within the monsoon season. It can happen in July or it can happen in August. And third one is the no decay. So there is no decay. For example, your 14, 15. So and 86, 86, 87, kind of that. So you have a bunch of those years in the historical data. When you consider them, what you would see here is that the red one is a early decay in observations of Nino 3.4. Nino 3.4. So before spring, that is going below zero. Anomalies are below zero. And when you see the mid decay, the anomalies are below zero only within the monsoon season. But in another composite, what you see here is a no decay of El Nino. So there is a three categories. One is the early decay, we call it as a mid decay, and no decay. So associated with this, the response of tropical Indian Ocean is also slightly different. So tropical Indian Ocean warming also decaying faster, but after monsoon in early decay, and it is further late in mid decay, and there was no decay in TIO warming in no decay of El Nino cases. So when you look at the month-wise variations of early decay years, what you would see here, when there is early decay by next summer, so June itself La Nina is developing and you could see very weak anticyclonic circulation here. Tropical Indian Ocean warming also seen in the northern parts, but in the western parts you don't really see. So moisture availability is quite low, so obviously you would have kind of less precipitation. So this is what is seen in the June. So as you go on to the next month, the La Nina is developing, its influence is high, the strength of anticyclone is strong, so you would see a trough region is getting low, but other parts of Indian monsoon region is getting positive rainfall. So overall, if you see in the early decay, you would see better monsoon rainfall over the Indian summer monsoon region. So these are the responses in both SLP and the moisture, etc. And when you look at this, this is the changes in ISM, subseasonal rainfall, as we have discussed, highly related to large scale circulation, which is reflected in this 200 HPA velocity potential. You can see that. In response to La Nina during the early decay years, this upper level convergence is seen here in the Eastern Pacific, and divergence is seen in the Western Indian Ocean. So these divergent anomalies and whole system is just moving towards the east, as you carefully see. So this actually has a strong impact onto the monsoon and enhancing the rainfall over the Indian monsoon region. When you come to the mid decay, so in mid decay, what do you expect? In the early monsoon months, you would see that El Nino is persisting, and that related warm anomalies can suppress the rainfall over the tropical Indian Ocean, North Indian Ocean, and Indian subcontinent. So this is, for example, 2016 June. So you have a kind of deficient monsoon in June itself, because that was the decay phase of ENSO year. So when it was not decaying much faster, what you would see, the easterlies can suppress the rainfall over the monsoon tough region. And here blue color is a negative anomalies, here red color is a negative anomaly. So there is some association in 2016 with mid decay of El Nino. So as you go on to the next like subsequent months, rainfall slightly like positive in some parts of tropical, in some parts of Indian subcontinent, because ENSO is gone. Indian Ocean start reacting along with the Western North Pacific anticyclone. And when you come to the last part where there was no decay, so obviously you would see that this El Nino is going to have strong impact onto the Indian summer monsoon through a well-defined water circulation and weakening of LLJ, etc. So basically, when you look into all these in the seasonal point of view, when you have kind of early decay, what you would see is positive rainfall over the Indian summer monsoon region, and mid decay is kind of normal. It won't be excess. It won't be excess, but when it is the no decay, what you would see that there is a deficit Indian summer monsoon rainfall. So this clearly suggests you that decay phase of variations in decay itself can influence the Indian summer monsoon rainfall distributions. And this is a schematic that represent all these processes in a single diagram. So you see that La Nina developing ED cases, and it will have impact onto the positively onto the Indian summer monsoon. And mid decay, first 2 months you have El Nino impact more, and after that you have TIO warming and Western North Pacific warming impact onto the monsoon. And as you go to no decay, TIO warming is almost passive, and El Nino is very active, and hence you have deficit Indian summer monsoon rainfall. So we looked at the same aspect in CME 5 models, and what we see is all these models are able to capture very nicely the variations in a decay phase. So first, there are a number of models, and each model is individually analyzed, and each model composite is considered here. So black one is observed, and the red dots that represents MME, and others are individual models. So models are able to distinguish the La Nina, El Nino decays. So when you see the impact in the early decay, obviously what you would expect is the La Nina, and associated with rainfall is kind of positive in the Indian monsoon region, where you can see the observed one, figure A of right hand side, and all of those you can see some models are showing positive Miro 5 and some other models. So but some models like CAN ESM2 has kind of negative monsoon rainfall, even though there is El Nino. So there we can see that there is some circulation patterns are not well going with the observations. So there is a large scale circulation response to the developing La Nina, and Western North Pacific suppressed convection is not really clear in those models. But when it comes to mid decay, so you would expect to have warming in the tropical Eastern Pacific. That is what we see in all models. And associated with this dipole pattern should be seen in the rainfall. But I think none of those models are able to show. I think only one or two models are able to show this dipole-like pattern in the rainfall in mid-decay case. When you come to a last one, which is the no-decay case, where you generally expect to have a negative rainfall over the Indian subcontinent. That is what happened in observations, and models are able to do a very good job, particularly in no-decay case. That means the models are like skills of these models in representing the variability of Indian summer monsoon is highly dependent on ENSO. So this is not just on the seasonal time scale. I just show I think last few slides talking about the sub-seasonal variations impact of Northwest Pacific onto the Indian summer monsoon. For example, when you go to this 2016, this is observed rainfall for JJA. You can see there is enhanced rainfall in July and a weak like negative rainfall in August. And green one is CMAP, like CMAP. There also we can see that there is a negative rainfall. But CFS model, what it showed was in the, like hindcast, it was like above normal rainfall throughout the year in all 4 months. So what was the problem in that model? So when we see the observations here in the left side, so it was a decay phase of El Nino 2016. So what we expect is anticyclonic circulation. That is what we have seen, and associated rainfall distribution also indicating a very nice pattern what we have discussed at POC. And July slightly changing, and by August it should have increased the rainfall when compared to June and July, but it suddenly went off to the negative rainfall anomalies in August over the Indian summer monsoon region, most parts. So what we have seen is this is basically not because of Indian Ocean response, but it is highly related to the Western North Pacific convection. So in August, we have seen that these convective activities are so strong that could influence the Indian monsoon rainfall, in particularly in August. So this is all in observations, but when you come to the model, so particularly in the August panel C, you would see nothing in the Western North Pacific. So the rainfall is obviously positive as we expect in a decay phase of El Nino. What we did was just again, we have done experiment in a coupled model. First one is observed August rainfall of 2016. So you see blue colors where negative rainfall and a bit of positive rainfall in the trough region. But in CFS V2, control run is showing everywhere almost positive except very small region, which is not going well with the observations. So when we introduce this kind of warning, as you see in D in the model, so there is enhanced convection in the Western North Pacific. Of course, this would have been a little north, and then what you would see kind of a belt of a little narrow band of positive, and other sides it is a negative. So from this coupled model experiment, it is very clear that the model, if it is able to capture the variability of Western North Pacific circulation even in the subseasonal scale, it would help to like forecast your or give better predictions of Indian summer monsoon rainfall. When we initiated the model in the just beginning of the August, what we have seen model convective activities are persisting till 18th, and then it's gone. Sound disturbance again. Shall I continue, madam?
Sorry?
Okay,
Hello?
shall I continue? Yeah, okay.
No problem. Carry on.
Yeah, so in observations, what you see, the convective activities last for I think 3 weeks, but in the model, it is just less than 2 weeks. So this is the reason why the forecast went wrong in the CFS B2. So what Wang et al. Suggested is that the monthly internal anticyclonic circulation changes can arise because of the ISO kind of things. So internal variability within the atmospheric circulation can even alter the anticyclonic strength. So that can influence the Indian summer monsoon rainfall. So just a slide I want to show on this PJ pattern. Just we have discussed the Western North Pacific impact onto the Indian summer monsoon. So even without tropical Indian Ocean influence, PJ pattern can develop, and that can again influence the Indian summer monsoon through the mechanism of suppressed convection in the subtropics and enhanced rainfall south of it through westward propagating Rossby waves. So overall, these studies, like our few years of research, definitely shows that the importance of IPOC mode onto the Indian summer monsoon rainfall, especially regional patterns. The best example is this year. And yeah, these are some references if someone wants to look into. Thank you.
Thank you, Dr. Jasti Garu. There are some questions from the participants. Uh,
Let
from
me
Gokul. Gokul, you can
go
ask
for
him
receive.
directly.
Could you please explain the impacts of what is the impacts of?
Dry
Yeah,
and moist Crosby waves on the peninsular in India rainfall alarms. Yeah, you can ask directly. You can ask
yeah,
directly.
Yeah, Gokul, that is simple. When you know about this gill pattern, mosquito gill pattern, when you have equatorial heating on the equator,
yeah.
you would see that two Rossby waves north of that, northwest of that, and one Kelvin wave to the east. So that is the mechanism exactly it works for this particular case. That you can see even when you have strong El Nino.
Yeah, sir.
In the
Yeah, yeah, yeah.
this is very well known
Yeah, yeah,
relationship.
yeah, yeah. But in one of your slides, you had showed the dry Rossby wave coming from.
Yeah, so you put your heat source to the north of the equator. What you
Okay,
would see the response to northwest of that. That is what you might have heard even monsoon desert mechanism. So you put either dry or wet convection in the north of the equator or away from the equator, you would see this values propagating.
okay, okay, sir. Okay, thank you.
Uh, Mr. Satish, you can ask him directly. Satish, does La Nina occur after El Nino?
Okay, it is not always, but generally strong El Ninos are followed by La Nina. So there is asymmetry in the transition period, like transition of El Nino to La Nina. So all La Ninas, when they decay, it becomes mostly La Nina for a couple of years. So what you would see more of them are kind of multi-year landmarks, for example, 99 to 2001 and 11 to 13 or something like 10 to 13, 10 to 12, I guess. So there is you can't say each El Nino decay can be a La Nina. So that is why I showed you there is a kind of variations in decay itself. So some goes for La Nina, some goes for like continuous El Nino. Yeah.
And one important question from the Lakshman. According to Clesius-Clapeyron equation, the capacity of air is to hold moisture increases by 7% of each degree of warming. In the
Mhm.
southwest monsoon season, some parts of India experience heavy rainfall and also flooding occurs in some regions. Is this due to the climate change or any other condition?
But point is here what scale you are looking at. So here I am looking at annual time scale. Definitely this point is valid for climate change studies. I'm sure there are many papers you can look into.
There is a question from Purna Durga. I would like to know, uh,
I would
can
like
we
to know,
estimate
can we
future El
estimate,
Nino, La Nina from CMIP feed datasets? Is that reliable to project?
I would like to know, can we estimate future? There is a all Simplify model gives you projections. So obviously, we would know what is the frequency of El Ninos or La Ninas using any kind of projections. You have a number of projections. So you can estimate the frequencies and magnitude definitely.
So another question from Bhagyasri. What is the difference between monsoon disturbances and semi-permanent monsoon systems over India?
Oh, this is obviously disturbances synoptic scale. That takes very a few days, like depressions and all. But the monsoon semi-permanent systems are almost there for a whole season.
That's good.
Hope
Uh,
that is fine.
and one more question from Kusuma Neti. Thunderstorms are mainly associated with convective clouds, but monsoon clouds are stratiform. Recently, I observed thunderstorms in monsoon season. Why it happens? Very good question.
Yeah, it is good, but point is that if monsoon is not extended and monsoon clouds are extended to all the regions, you would expect definitely because moisture is high in some of those regions. So you would expect thunderstorms. That is also actually part of the monsoon.
Yes. Narayan Reddy is asking, sir, when occurrence drought are more possibility during canonical or monarchy? That means he is
Oh,
asking about the occurrence of
yeah.
drought.
Actually, what happening when there is a canonical end, so El Nino, sometimes it co-occur with IOD. So obviously, you don't see kind of very strong drought. But when there is a Modiki, they are not coincide like tied with IODs. So or equino whatever. So definitely you would see some kind of drought or like even Ashok et al. And many others showed that frequency of these Modikis are increasing, and that is why you see recent years some of those droughts like 2002, 4, 9. So yeah, when with the canonical also, if there is no IOD, you would see that drought is happening. But when Modiki, mostly it is going to be yeah.
Uh, and the question from Purna Durga again. She's asking that I have a 19 global climate model. If I would like to estimate future El Nino, should I consider historical data sets or can go with climatology of future projections like RCP 4.5 and RCP 8.5, etc.?
Okay, so for projections, you need to compare historical, present and future. So she need to take all 8.5 or whatever, like all scenarios, and then do the analysis. I think the best way is these days not CMIP files. People have started analyzing CMIP 6. If we even do CMIP 5 analysis, definitely reviewer is going to ask for CMIP 6. Yeah.
Anyway, that's it. So thank you so much, sir, for your valuable and excellent presentation on monsoon variability with connection with the Pacific Japanese pattern. So really very much thankful to you on behalf of the participants. This is a very good topic in the present scenario. The people will get inspired by seeing you how the variability and all these things are really matters in predicting the Indian summer monsoon rainfall. So you are also one of the inspiration to our students. So thank you very much, sir. Keep going on good work. Thank you.
Thank you, ma'am. Thank you very much for invitation, and it's my pleasure to you. Yeah.
Uh, Dear guys, tomorrow is the Independence Day, so don't think that it is a holiday for you. Tomorrow, Dr. V.S. Naidu is going to present you, and afternoon there is a tutorial by Dr. Professor B. Munuswamy from Department of Statistics. So he will give you some glimpses of R. Okay. Uh, Regarding the presentations, we will share the presentation after the course. Okay, after 25th. Thank you very much. Meet you soon today. Tomorrow, sorry.
Okay, thank you.
Thank you.